Welcome back to the shrine and Happy New Year. On the altar today is a ceiling fan that was given to me by a friend. He said that it's not working, and I was just curious in general what can possibly go wrong with machinery like this that is ubiquitous. You go in any house, there's a couple ceiling fans, and they've been around for a while. You would think that the manufacturers do a good job of making them bulletproof, but as it goes, there's different varieties and levels of ceiling fans. You can get one for $50, you can get one for $1,000, and there's different I guess component levels and bearings and electronics in it. So what we're gonna do is take it apart and have a look inside. But before that, you can see this is a pretty complex machinery. So it's not just a simple wedge that you would stick in a piece of wood to rip it apart. It's got a bracket up here. This is what you use to mount it to a stud, and then the fan part is just below that. This is what called an Outrunner motor. So the stator is stationary and the rotor that's spinning, it's on the outside. Right here underneath we have a box with switches. So there's one switch on the side, there's another one here which is a pull switch, and then underneath that we got a light fixture which has 3 sockets, and then on the side it has some warning. It says maximum 40 watts, and you can see some of these insulation here is discolored. Okay, so the bulb would sit in a socket here, and it's near this insulation, near this zip tie. You can see there's discoloration on the zip tie. There's discoloration on the insulation. Same on this one, same on that one. So whoever used these might have put a larger power bulb in it, not just a 40 watt. Or maybe, you know, if you put a 40 watt, it will create this discoloration. This is glass woven insulation tubing, and typically it's impregnated with some kind of varnish, and so the discoloration that you see, that's the varnish is having a discoloration. So from the fan we got a couple wires here. So this is the ground wire. You can see that this is grounding everything. That's the green wire. We have a live wire here which is the black, and then we have a white wire, and then the blue one here has a label. It says LUZ, light. That's probably Spanish or French for light. So the first thing I'm gonna do is just do a continuity check. Grab a meter, put it on resistance or continuity. So wires, terminals like so, and then do some switching. So it's not beeping, but it's showing 118 ohms. Turns everything off because it's 0. Okay, so 120 ohms, let's see. And when I'm spinning it, you can see the resistance is changing. So that's that. What's happening is when this rotor is spinning, it's inducing current, and that's an AC current, because these if there's magnets passing by the stator, they are inducing current. So when this is moving, then we can see the resistance is changing. So I'm gonna go and just pull this switch, and you can see that turns it on and off. So there's the other one, nothing. Third one, nothing. And then number 4 goes back to the original resistance. So this is probably adjusting the speed, and some of the speeds probably not working properly. So we're gonna go and take it apart, have a look. Not so tough anymore, right? There's always a larger wrench. I'm gonna go and look inside the motor, see if there's anything burnt up, but otherwise I think we'll need to find a culprit here in this box, the switching box. There are some labels here. There's a caution label to reduce fire risk. There's a file number here. Looks like this is just a general fan. There's not even branding on it. Made in China, of course. 60 watt, half an amp motor, and 3 light bulbs, maximum 40 watts, 1 amp each. 44-inch ceiling suspended fan. So these ceiling fans come in various sizes. So you can buy them at 48-inch, 54-inch, 36-inch, and depending on the size, the motor is gonna have different speeds. So there are typically 3 speeds for the motor. There's a normal. So the normal speed for a 44-inch fan, I'd say it's about 350 RPM. If I do some head calculation, that would be a 20-pole motor. So the speed is 120 times the frequency divided by the number of poles. So the frequency in the US is 60 Hertz, and then the speed, let's say it's 360 RPM, so this should have about 20 poles. That's my prediction, but we're gonna go and have a look. Okay, we are inside. So this is the rotor, as you can see. It also called an Outrunner. This looks to be aluminum, and you can see inside here it's die-cast aluminum, and then this outside part is lamination. So what lamination is? It's just thin steel, basically packaged, and then what they do is they put it in a mold, and they're gonna cast this aluminum into it. And then right here you can see that the lamination pieces are interlocked. So this is an interlocking feature. So this is done in order to make this a fast assembly. So you would think that people who are manufacturing this, there's a stamp, and then these lamination pieces are coming off of the stamp of the stamping machine. So someone has to take them one by one and stack them and measure the stack height, and then in some ways retain them together for the next machine that is gonna create this casting in a process. So to prevent this loosening or being just a loose lamination, an individual lamination, they add these features here. So what these features are, they just cut out from the lamination itself. It's got a hole here and it's probably skewed, so the skewing is gonna stair step the lamination, so it's skewed in an angle, some kind of angle, and then they just press them together so these features will interlock the pieces, so this outside lamination will become one solid piece. So inside the motor, this is what we got. So we have, as you can see, two windings. So this inside winding, you can see, is separate from this outside winding. Okay, so what we got here is two different winding. One is the start winding, and then one is the running winding. And we need that because this is a single phase machine. So in a three-phase system, you would have a traveling wave in the coils that moves around, and it basically drags the rotor with it. But in this one, we only have one phase. So this is a pulsating magnetic field rather than a rotating magnetic field. So if you are sitting here on the rotor and looking towards the lamination, you know, what you can see is that magnetic flux, you know, it's proportional with the voltage. That flux goes up and down, but it doesn't travel in space. So in order to be able to move the rotor, we add the secondary coil, okay? And what it does, it's phase shifted. So the way we do a phase shift is we put in a capacitor, and when this coil is energized and this coil is energized, it's going to create a drag, and it's going to start spinning and rotating this rotor. Okay, so you can see the terminations here. Okay, so what we have is we got this shaft, and then these three wires come in. You can see we have basically the black and the white wire, that's the power, and then the blue wire is for the light. So these three wires come in, and you can see this shaft open right there, and a package of wires come out. And so in this package, in this bundle, we have basically 4 wires. So we have a red wire, then this is a gray, a brown, and a white wire. So these wires go down into the box, and then from the box we have 4 wires coming back. And so what it does, it will tie to these wires. Okay, so what we got here is 2 different size wires. We can actually go and measure the size. So you can imagine that the starting wire is only working when we start this thing, and then the running wire is on constantly. So the running wire has to have a lower resistance, and then the starting wire has to have a higher resistance. So typically the inner coils are the starting wire, and then the outside one is the running wire. So let's do a measurement, maybe right there. So the outside wire is 0.26, and then the inside wire is 0.29, 0.28. So the inside wire looks to be a heavier gauge. Now if you do a pole count here, So 16 poles, 16 coils on the inside, and most likely 16 on the outside because it seems to be symmetric. So yeah, 16 on the inside, 16 on the outside. So let's do the calculation. 120 times 60 divided by 16. So we got 450 RPM. So these are typically, you know, the laminations are made out of some cheap steel, but if you are buying more expensive fans, then they are typically being done from silicone steel, and then the thickness is different. Now if you look at the laminations here, you can see that they are fairly thick. They are in a range of 1 millimeter. But if you want to have less losses, higher efficiency, then you go to a thinner steel. Well, I can also see that the stator is made from the same gauge. So there are some holes here. I think these are for ventilation. What they do is they ventilate the fan, so there's an airflow that's going in the axial direction, and it's cooling these parts. So the fan is churning the air in the room. That's what it's designed to do. But if you look carefully here on the cover, you can see these scoops. So when the fan is spinning, these scoops will induce an airflow. Okay, they will grab into the air and basically move air in the axial direction, and that's what they use to cool the motor. Because at the end of the day, what we do is we are running current through these wires and coils, and that current is gonna heat it up. Now, if this would be an intermittent duty, which means that you turn it on, you turn it off, then because we have a thermal mass here, it would take some time to heat it up to operating temperature. But typically the ceiling fans are running, you know, sometimes 24/7 for years. If you go down to the Gulf Coast, you can see, you know, on some of those houses, the fans are on basically day and night. They never turn them off. Also over there, they're probably not using this metallic or steel housing. They actually did a real poor job of painting this. You can see on the outside it's nice and black everywhere. The paint looks nice, but on the inside you can see the primer. I'm not even sure if it's the primer. It might just be the bare metal. So this cage here, where the bearing sits, this is definitely not painted. So what they do is they deep draw this and then they trim it off. So here the edges are so sharp, you know, razor sharp, and then they're just gonna go and paint it. But I'm not even sure this is electrostatic paint. I think it's just some kind of spray paint, because I can see areas that the paint just didn't adhere to. Let's take this section apart and see what's inside. So here on this side, you can see it's fairly simple. So what we got here is we have a simple switch. So when someone drags this line, you can see it turns the switch on and off. And all it does, it just cuts the power to these bulbs. So here is a so you can see that all the white wires are bunched together, all the black wires are bunched together. So we got a black and a white wire coming through from that side, and then the black wire that comes in, goes through the switch and then goes into this junction box, and then from the junction box it goes to all the 3 different sockets. So all this is just a switch. There you go. Okay, so I was right. Looks like that this cover and this cover, you can see they are bolted together. So there are 2 wires heading out that way. Looks like there's a quick connect here. So they just plug them together. I'm just gonna try to disconnect these 2. They'll probably fight me to the grave. Okay, remember kids, the black wire goes to the blue wire, and then a white wire goes to the white wire. So that is disconnected. Okay, it's done. So what we got here? Okay, so these are the 2 wires that go to the light. You can see we have something big here, big and bulky, and then we have the switch. Okay, so through the hole we have the black wire. Okay, so I'm dragging on the black wire here. You can see it's moving here. So this is where the black wire is terminated. It goes into this switch. Okay, and that black wire goes either to the yellow, orange, or the purple line. So what this switch does, it will connect the black wire to one of them or a multiple of them. So here's the white wire. Okay, there's the white wire. You can see the white wire just comes in and goes into this bunch. Okay, goes right into that bunch. So what it does, it's just being distributed to the light and to this switch. So you can see this switch here, it has 2 different positions. Okay, maybe on and off, something along those lines. So if you look at the switch, you can see that the white wire is in the center and then the orange wire is in the center. So what this switch essentially does, it will connect this center prong to this side or that side. And so we have 2 banks here, so right bank and left bank, and they are separate from each other. So this side never touches that side. All the switch does, it just connects the center to this end or to that end. So it looks like on this side the switch is connecting the white to the gray or the brown. Okay, we got just 1 too many wires here. So back into the shaft goes 4 wires here. So we have a thin white, red, brown, and gray wire. So those are the ones that feed into the motor. And so we have a big capacitor here. That doesn't really look good. You can see it's got these deformities on the side. So what we got is we have power coming in, and then that power goes through a switch here, and it's being routed to the coil, and it's being routed to a parallel coil. Remember I said inside here we have a starting wire and then we have a running wire. The running wire is on all the time, and then the starting wire goes in series with a capacitor. But what we have here is we have 3 speed. So for each speed this switch is gonna turn a different starting capacitance. So on this side we have two orange wires, and then here's a diagram, okay, and then on that side we have a yellow, a purple, and a red wire. And if you connect to the orange wire and then the yellow wire, which right here it says Y, then you're gonna get a 6 microfarad capacitance. Then if you connect to the orange and purple, which is the center one, you're gonna have a 6 microfarad capacitance again. And then if you connect to the orange and then the red here, you can see the R, letter R, then you got a 4.25 microfarad. So I think what happens here is they're gonna hook up either 6 or 6 plus 6 or 6 plus 6 plus 4, 25. Or maybe they're gonna hook up 425 plus 6 plus 6. So this is gonna be first speed, these two will be the second speed, and then these three will be the third speed. So in that case, two of these capacitances will be connected in parallel. So if you look at the capacitor here, you can see that it's burnt out and it's bulged out. I'm positive that it's not supposed to do that. Okay, not supposed to bulge out like this. It's supposed to be flush on all sides. So what most likely happened is this capacitor got overheated, and when it overheated, you know, it basically just fails. It fails to open. So you're going to have an open circuit. You can also see on this side, okay, there's some traces of reflow. The plastic on the capacitor housing got reflown. So as the wire presses and the wire overheats, you can see that that capacitor housing overheated. That's that's basically it. I can go and look it up and see if I can get this part number and repair it and replace it. But my buddy already bought a new fan. Again, you know, these fans are commodity. You can buy them anywhere for real cheap. So I just googled CBB6-1 and Google automatically shows me 10 microfarad, 20 microfarad, new ceiling fan capacitor CBB6-1, 4.5 microfarad, 6 plus 5 microfarad. This is funny because this has 425, 6 and 6. $7.99 free shipping. It'll be here in 2 days. And looking at the pictures, it doesn't look bulged. If you have the same kind of issue, I think it's worth fixing it. I mean, we are looking at a basically $8 expense and a couple of wire nuts. So the first thing would be to go and cut the zip tie, and then the next thing is you have the new capacitor side by side here, and you come in with pliers and you're gonna go and open these wire nuts just like that, and then once it's open, okay, you can pull it off. So you can see how the wire nuts are attached here. So at this point you can either use the original wire nuts, uncrimp them, and then go through that jazz routine, basically pull this off. You know, use some kind of a method of fastening the wires. It's really important that you go and attach the wires the same way as they were. attached earlier. So red goes to red, you know, purple right here goes to look at that, the purple is attached to the box, so this will have to come off like so, and probably take this cover off. Just plugs in. I'm at loss at this point. So you can see what I'm struggling with. So this purple cable that comes from the cap, it directly attaches to that. So I think what I would do is I would cut this wire and just use an extra wire nut. You would go through 4 or 5 different wire nuts, or you can solder the joints together and put some tape on it, and that would be that. So you know, this would work again. So it looks like we have 5 wires here, and we got the orange wire, and then we have another orange wire here that's connected to the switch. And then we have the red, the purple, and the yellow. So it would require at least five of these cable connectors. So there are various cable connectors. You can use this connector assortment. This is from Horror Freight. There are these little connectors. So what you do is twist the wires together, put this on, make sure it's secure. There's also this style. Okay, this is a crimp-on. So you got one wire coming from one side, one from the other side, and then you use some kind of crimping tool to crimp it on. And what this does, it will secure the 2 wires together. It will also isolate the wire, electrically isolate the wire. It's really important because this whole thing is metal here, so you don't want these wires to touch the metal. So there's different sizes for that. There's this, you know, big beefy one, there's this small one. There's other methods to do it. That's pretty much it. I'm not gonna fix this. I'm just gonna put it in one corner of the shrine, and one day we might come back to it and create a science project out of it. I mean, it's still a good motor, and it has one speed that it runs at. By the way, these capacitors are not polarized, and typically their capacitance is 4 to 6 microfarad. That's what I've seen earlier for similar motors. I was always wondering about these fans, you know, if the fans rotate in reverse direction in Australia or in Brazil. So if there's someone from Australia or Brazil, you know, if you can confirm it, I can tell you that this is mounted such a way. Okay, so the scoops are pulling in the air this way. So if you're looking from the blade side, from the bottom, it rotates clockwise. So I was always wondering if they make special ones for Australia that rotates, you know, counterclockwise in the opposite direction. This bracket is interesting. If you notice, there are these bushings here. So there are these, it looks like rubber, but it's really just hard plastic. And so when you mount the motor to the stud, you know, the bolts or nuts or fasteners will go through these holes. So the plastic is going to be in a clamp, and you can see that these parts don't come off. They are an integral part of the bracketry So why is it there? They put these for dampening purposes. If you can imagine, when you take this fan and you mount it to a big flat surface, it acts just like a piano. You know, the piano has a soundboard, so your entire ceiling surface is gonna act like a soundboard in the piano. So if there are any vibrations coming through, that will amplify it. And so there are vibrations here. You can see that everything is connected to the same central shaft, and the shaft is bolted to this, so there's a good transmission path. And so that's why they put the dampeners on. For more expensive fans, I'm thinking, you know, there's just different rubber dampeners. Actually, the stiffness and the hardness of the plastic or rubber that they use is going to define which frequencies it will dampen. The other thing that came through my mind is that when this is not running because of the capacitor issues, then it's just going to sit in one spot and buzz. So if you have one that's turned on but it's not running and you're not aware that it's turned on, then it will give out a buzz. But if you don't catch the buzz, you're still running current in that primary coil. And because there is no movement from the rotor, it's not generating airflow, it's not cooling it. So this buzzing is really a double-edged sword. From one standpoint, it's bad because it makes noise. If you put this in a bedroom, you know, you're gonna hear it in a bedroom. From the other point, if it's not running, if the fan is not running and you don't realize that it's turned on, it's just gonna give out a weak buzzing sound. You might not catch it on time before, you know, something else might happen, like some kind of thermal event. Let's put it that way. So I'm trying to see at what temperature this is going to start melting the plastic on the capacitor. The soldering iron is at 350 degrees and it's melting. It's slightly, but it's melting. That's the lowest setting. So 350 Fahrenheit is gonna melt this plastic. You can see that it's melting. It's got a smell. So 350 Fahrenheit is 177 degrees Celsius. So that's basically below ABS and a little higher than PLA. Okay, so what we got here is we got AC coming in, and there's one coil here. So that's the running coil, and then here we have a capacitor, and then we have a starting coil, something like that. So this is the rotor. So this capacitor here, that is the one that is housed in that black housing, basically, and the value of the capacitor can be changed from 4 to 6 microfarad. So what it basically does, it creates a phase shift for this coil. So if you look at the sine wave, it does something like this. Okay, that's the primary wave that comes from the AC side. Now when we implement the capacitor, what happens is the capacitor it's basically fighting the change of voltage. So there's going to be a voltage, you know, so this is an inductance here, there's going to be a voltage on the two sides of the capacitor, and it's going to fight that. So you can imagine this like a bucket. So you have a constant flow of water here, okay, and then some of the extra water is going to go this way, fill up the bucket, and then once the bucket is filled up, then more water is going to go this way, and it's just going to repeat the cycle. So what this cap is doing, it's going to offset that secondary wave. Okay, so this secondary wave, you know, that's what's going to make the rotor to move. And if I put a different capacitor here, this distance is going to change. That offset is going to change. So it can be 9 degrees electrical, or it can be something else. That's how the speed is varied. You know what's coming. I had to do it. So we're going to go and just run a test and see if it's buzzing, what kind of other sounds, noises it is emitting. I'm basically ready to plug it in, but before doing so, let's just do a safety check. Okay, should be good. And I should be able to drag on that. Okay, so the rotor moved. You can see in these specific positions, it's just buzzing. It is just buzzing. It's not really doing anything. It's trying to turn, trying to rotate, but mostly it's just buzzing. So I'm gonna go and you can hear that. That's probably off. That's probably off too. Okay, here's one speed. Here's another speed. So nothing. It's not running. Yeah, I know it's missing one of the covers here, but it's not running. So what I did is I went ahead and I looked in my local store. So sure enough, this is probably a common issue. They keep these in stock. I paid $7.99 plus tax, 7% in Indiana. Patriot lighting. You can see ceiling fan, triple capacitor. I'm pretty sure Home Depot carries it. Lowe's carries it, or any of these big box stores. So it says CP 2001 50-60 Hertz, Menards Inc. ceiling fan triple capacitor. Okay, it's got the Menards part number on it. So 345-8034. So I'm gonna go and pop this open. And you can see these nice people. They not only included the capacitor here, but they also included wire nuts. So if you buy this, then you're not gonna have to deal with like trying to figure out where you get the wire nuts. So at this point, what I'm gonna do is I'm just gonna you know, cut these wires here, especially the ones that have the wire nuts on them. And I'm just gonna go and one by one replace all these wires. So 2 wires are connected, you know, red here and red on that side. So what I did, I just cut that off and just connected them with a wire nut. So here's one, for example. Here's the purple. You can see the purple is coming out from the center here. I'm just gonna go cut the purple line just like that. Okay, and then I'm gonna just remove the insulation, take the purple from the new cap, and then put them side by side, twist them together, get a wire nut, and just attach it like so. So I'm keeping the old capacitor and the new capacitor side by side, so I can go and change these one by one. Interesting is the purple here is center, and then this is brown, and then this is yellow, and that's purple. So I think I need to go center to center. Okay, we can give it a shot. There you go. So these wires are thinned. They are thinned up. I think they are made ready to be plugged in to some kind of receptacle. Okay, here is. Okay, the red one is already connected. There's the purple, so that will go to the yellow. So again, I'm just gonna go here, cut that yellow line. Just remove insulation, hook these two up, like so. Put the wire nut on. And then all we left are the two, these are orange, but these are gray. But essentially, you know, these two have to be connected to this. So I'm just gonna go snip, snip. Like so. Twist them. Put the wire nut on. Okay, and then the last one you can see is this. It's just probably plugged in, but I don't want to play with this switch, you know, removing the cover and then trying to figure out how is it attached there. I'm just gonna use the wire nuts, especially if you're doing this in a bedroom. You know, when the fan is still attached to the ceiling, make sure you disconnect the fuse. You have your wife standing by, she's holding the light so you can see, because this is the only light source. You know, typical stuff. So I'm gonna put it back like so. Plug it in. Well, sure enough, you can see she's running. So I don't have the other side attached, and that's why it's wobbling. So I'm gonna go and put it back on and then do some testing. Installed the cover back, just added a zip tie here, installed this switch, and this is some double-sided tape. So you might remember that the original capacitor had some double-sided tape on the bottom. That's how it was attached, so that it wouldn't rattle. So there's a double-sided tape. I'm just gonna remove the applicator and then glue this back on right where it belongs, right there. Okay, that should be good. These wires go back to their spot, and now I can put this all back together. But before doing so, I wired it up, and let's do a test. So you can see it's running, and I'm changing the speed, but of course there's no load on it. You know, there's no fan blades. So that's the off. You can see it stops. This is probably the fastest. And there's some hum. I can hear the hum. Okay, so in this first speed, there's a definite hum. The second speed, less hum. And then the third speed is the quietest. So I call that a good surgery. The patient survived. He was actually resurrected right here in the shrine. on the altar. Thanks again for stopping by. Hope you guys learned something. If you like the video, please give me a thumbs up, and if you like the channel, please don't forget to subscribe. See you next time. Bye.